So, hello everyone, and thank you for coming here, and thanks for having us as well on this beautiful day in Las Cruces. So my name is Peter Kronos, and I'm the founder and project lead of ARES' rocketry team. And the focus of my team's presentation today will be on the design, analyses, and manufacturing processes of our variable diameter 10,000 feet solid fuel commercial off-the-shelf sounding rocket, which is named Phobos. And without bragging, it's one of the most optimized rockets we've ever made. But of course, we've only made 2 rockets, so that's the thing. So the team was founded in 2020, and in our limited time around, we've been able to build 2 high-powered rockets for competitions, and Phobos is actually the first competition rocket that we're flying within a competition, that is. So we've got 48 active members on the screen. Here you see the members that have come to America to actually assist the team in the mission of launching. So we've got 6 current subsystems, those being the aerodynamics, avionics, flight simulations, payload, structures, and operations and logistics. So just a quick overview of what today is going to be like in terms of items in the agenda. So first we'll have a brief overview of the physical characteristics of the rocket and also the components inside the rocket. Then we'll have a quick explanation of the payload, which is the reason behind the transition that you're seeing on the screen there. Following, we're going to have an overview of the CFD simulations and methodology behind the simulations, as well as all associated outcomes that have come from these, again, simulations. A detailed explanation also surrounding the manufacturing processes is going to be given to us by Kian. So that's along with any design considerations that we had to take into account as we came up with this novel kind of design, transition design. And at the end, we'll summarize all the main points and kind of take any questions you may have. So I'll pass over to Harrison now for the next slide.
Great. Thanks, Peter. And I'm here to just give a high-level overview of the entire rocket. So it's essentially 9 feet, the 2700 mil, and the 90 mil and 160 mil external diameters are what the transitions formed to meet, with a laid-up fiberglass airframe, plywood bulkheads, and G10 for all the fins and launch lugs. The motor is a L2 motor, which is maybe a bit unusual for the 10,000 feet challenge, but it's a 98% L motor. And we're running a SRAD flight computer just in parallel, but using Ravens, which will be elaborated on, and a functional scientific payload of 3U CubeSat form factor, which we're really set on and is the main design motivation for this rocket. And with that, I'll pass on to you.
Hi, my name is Ben. I'm the chief engineer, basically lead design for the project, and I'll basically run you through a little bit of our design considerations, why we made the choices we did. So first of all, as Harrison mentioned, our goal of making sure that we did adhere to the CubeSat format was the driving reason for why we selected the big bulbous fairing at the front. And then having limited motor access in our country meant that we had to optimize the drag of our rocket so that we could still get to 10,000 feet on just a sort of relatively underpowered L2 motor instead of an L3. So that's what led us to select to go from a 160 mil, roughly 6-inch diameter payload section down to a 90 mil, roughly 4-inch diameter main section. I will now just pass it over to our payload team to go a bit more in depth on that.
Hi everyone, my name is Rui and this is Neil, and we're from the payload team. So our payload is a mechanical model of the human neck segment of the spine, and the purpose is to investigate the effects of high G axial loading on the neck and what happens to it. So the motivation behind it is, so in high G flight, especially for fighter pilots, when you're experiencing sudden GZ direction acceleration, or say, for example, when you're pulling up or when you're ejecting from the seat, you're getting massive compression forces across the spine, and your cervical spine or your neck part is the most mobile part of the spine. So when you're flopping around and you get that massive compression, it's quite likely to cause injury. So our model is we aim to measure the forces between each segment of the spine and then essentially work out what the force loading pathway is, and work out what are the areas of the spine that are most susceptible to injury.
Yeah, awesome. Thanks, Rui. So I'll pretty much just go over the model we're using and how it sort of works in our rocket. So essentially we've got a 3U CubeSat, and the main purpose of the 3U CubeSat is not only just to house the scientific payload, but it's also serving the function of, so like this, the rendering you see on the PowerPoint slide is sort of an initial sort of concept for how it was supposed to work. And as you can see, it's slightly different to that initial design. But essentially, it's the spine mounted to a board and then a mass on top of the spine, which is acting as like a simulation for the head. And we designed in such a way that the mass sort of slides through those rails and the forces of the rocket are transferred through the spine. We've got these force-sensitive resistors that are placed between each vertebra, and there are about 15 of those sensors. So we're getting a lot of data across the whole spine. We're able to then model that throughout the flight and then look at that data later on. So to measure that, we're using a TNC 4.1, I think at 100 hertz to grab all those data points. And then the CubeSat frame itself is using aluminium angle for the side rails, which fit into this like dispenser. Not really dispenser, but fits into this fork system that holds in place. And then it's using 3D printed caps for the bottom to hold it all together. It's also got metal plates at the bottom and top to reinforce the actual structure. That's pretty much it.
G'day, my name's Josh. Apologies, first of all, I'm going to be saying words like millimeters and meters a lot, so if you've got allergies or anything like that, please protect yourself. So to fit Rui and Neil's payload into our rocket, we have to have a 160 diameter tube, but if we made our whole rocket 160 diameter, that increases the surface drag of our rocket too much, and so that means that as we are restricted by our L2 motor, we had to find a solution which ended up being this transition. The tricky thing about having a transition is that as flow moves around like a step down, it means that it accelerates, which means that even in transonic regimes, you can have localized regions of, thank you, sorry. You can have localized regions of supersonic flow where shocks are induced, which in the wake of that, the drag increases significantly. And so your shiny, fantastic transition, which is going to lower the drag of your entire rocket, is suddenly increasing the drag of everything, and your great plan is ruined. So to work that out, we have to find, there are two ways essentially to work that out. We either use a wind tunnel or we use CFD. And as our uni was not that keen on giving us $1 million to build a new wind tunnel, we decided to use CFD. We tested with five different lengths of transition, because that's essentially the only thing we could change given our upper limit and our lower limit of tube. As you can see here, the intensities, the shock intensity is much greater for the 400, much greater for the 100 length tube than for the. Sorry, I'm a bit nervous. The shock is much greater for the 100 mil length than for the 400 mil length, and so by using that new method, we decreased the entire drag of our rocket by 38%, as opposed to just using the 160 the entire length. We also tested a 500 long, which is not shown here, but given the fact that it made very little difference, we decided to go with the 400 because increasing any longer than that would just increase the weight of our rocket. And as we're only using L2, we don't really have that kind of room to throw around. Yeah, and this is just the pressure. And so, thank you very much. I'll hand over to Kian to talk you through how we made it.
Hi there, my name's Kian. I'm part of the structures team, and I'm going to be talking through how we actually manufactured the transition section. So all the way from where our avionics bay starts right through to the tip of the rocket was all manufactured as a single piece. This was done with a 3D printed mandrel for the nose cone, and then that slots into a 160 mil diameter PVC pipe that's about 120 mil long. That then inserts into a turned mandrel. You can see a photo there of me on the lathe doing some sanding. So we use jelly-tong for the mold. It's a really great stable wood, great for pattern making and stuff like that. So at each end of the transition mandrel, we have a 50 millimeter insert, which inserts into the neighboring mandrels. So the way we actually turn this down, obviously this is a manual machine, so you don't have any CNC abilities. The way we did this is that we turned it down to a number of key diameters along the length of the transition, and then blended between those, and then just sanded. And we actually managed to get the transition to within about a millimeter of our laser cut profile. So all of the airframe is constructed from 2x2 twill weave fiberglass, about 400 GSM. We went for a twill weave because it has better conforming abilities to compound curves, which obviously we have quite a few of on the rocket. So all of our booster sections and straight sections use a PVC mandrel. We went with PVC because it's super cheap and super available, and mostly straight. You can also, as we found out, chip it out of the fiberglass if it gets stuck, which it frequently does. So the booster sections and straight sections are continuously rolled onto the mandrel, but this wasn't possible for the nose cone and transition section because of the compound curves. So what we did is we took half circumferences and then laminated them together, and then offset the next layer by 90 degrees, and then the other layer by another 90 degrees. A big thank you to whoever put that terrible photo of me in the presentation there. So as you can see, we have our, as I mentioned, 3D printed nose cone up top, and then section of PVC, and then the lathe transition, and then there was another PVC pipe that slotted on the end there. So normally you wouldn't be able to actually extract these mandrels, but because we needed a separation point for the payload, we could actually cut all the way through our PVC pipe there at the top and remove the mandrels with a bit of force. Then, once we have the raw fiberglass, you want the best surface finish possible. It's a big contributor to drag on an aerodynamic body like this. So what we did is we filled any low spots with a body filler that you'd use for repairing a car body. This was then sanded back. So for the transition and nose cone sections, they were actually short enough to fit on the lathe that you saw there. And so they were sanded back on that to get the most round possible. For the booster section, just hand sanded as best we could because it was too long. Then after that, we sprayed with a high build automotive primer. So that fills in any little holes. And once you sand that back, you can see all the little pinholes that are left in the fiberglass. Then you can use a popsicle stick with some of the filler that we previously used, and you just dab it in and then just scrape off as much of the excess as you can, because it's a real pain to be sanding back loads and loads of filler. Once we'd done that, we used an acrylic car paint from our local, it's called Super Cheap Auto. I'm sure you have equivalents here. 2 coats of paint, sanding after each coat, and then the final sanding was up to a 2000 grit, and we're very happy with the surface finish we've got on that. Yeah, I'll pass over to Conrad. Thank you.
So yeah, my name's Conrad. I'm the aerostructures lead for ARES. These launch lugs, these were a very big pain for us to manufacture, and as you know, our decision to include a payload directly led us to needing the transition section, and then having the transition section meant we had to raise our launch lugs off to actually clear it on the rail. They're mounted in pairs to balance the aerodynamic forces, and they're mounted on the 90 millimeter diameter section of our rocket. They needed to be tall enough to clear the payload on the rod, as already said, and that meant we needed to finalize a design that was not only strong enough to bear the weight of the rocket, which is about 10 kilos, but it needed to minimize drag. We found from some early CFD results that having these launch lugs versus the null case of having just a smooth, normal body was an increase of drag of about 30%. So these needed to be strong and they needed to be aerodynamically profiled really well. So the design we ended up using was a structural M8 bolt through the middle of it. Very crude, but it does a very good job. Can bear the full weight of the rocket. That is bolted to the inside of our body tube. It has a backing plate, and then that was fully epoxied over, so it's a permanent joint. We then did a layup with another bit of G10. So the G10 forms basically a fin around the launch lug. We had one layer of fiberglass laid up over the top of that, and it creates a very smooth finish. And that was all sandwiched between acrylic and compressed really well. Turned out really well. One other thing, we did need a file down that bolt. It is M8, and we had to go from M8 to 3.5 mil, so that was a bit of a pain. The last thing we needed was the tab to actually interface with the launch lug. The one there is from a previous version. We realized a mistake somewhere along the line that we'd assumed metric was universal. Obviously not. So we designed it for a launch rail in Australia with a 10 millimeter gap. That wasn't sufficient. It was too small for the standard one URSA uses. So we've redone it. We made a little button, and that was turned on a mill. So we have an aluminium section that bolts onto the top there, just like the tab did, and then a nylon bit that was also turned down to really fit snugly with the rail. So in all, we achieved a lot of our goals in terms of the manufacturing. We've achieved the transition, we've achieved the fins, and we achieved a really good surface finish on those fins. Thank you.
So to conclude, in closing, we have achieved our two goals that we had initially, those being having a payload and using an L2 motor that we were restricted to using by having an L2 flyer, by optimizing the design of the transition so that we can have the lowest weight and drag, and avoiding these areas of very high intensity shockwaves around the transition that Josh talked about a bit just before. The second goal that we achieved was that, according to our simulations anyway, we will be reaching our target apogee of about 10,000 feet. So obviously that's crucial for the objectives of the competition. Additionally, on top of that, we've met the two requirements that we've had of needing standoff launch lugs, as Conrad just mentioned. Obviously, having the transition be bulkier than the rest of the body, we need standoff launch lugs to be able to fit into the rail. So that was done by the methodology followed by that was outlined by Conrad. And obviously the second design requirement that we met was having a transition to house the payload, which is what Neil and Rui described, which is going to be the medical payload, measuring the compression of the cervical spine. So with that, and just a small point there, that follow-on work is that we're looking into creating reusable outer molds so that we don't have to have, like Kian explained, having the 3D printed molds and having to destroy them to then take out the fiberglass. So that's something we're looking into to be able to use them continuously for other rockets into the future, and save materials and save time as well. So that is it for the presentation. Thank you so much for having us. If there's any questions, we're happy to take them. But yeah, that's all.
So yeah, questions, people feel free to come up to the front, have a closer look. I think I saw someone laughing about how they had similar problems with launch lugs maybe. Yeah? Honestly. Imperial units. Who invented that?
Significant increase in drag through your logo?
Yeah.
Alternative concept designs that can produce lower drag?
Very good question. So the question was, with the design of our launch lugs, how much does that contribute to our drag? And were there any other designs that could have reduced that? So I believe it was around about 30%. Thank you, CFD people. I think, yeah, around 30% of our drag is actually being generated by those sort of sticking out launch lugs there. So definitely a major factor from such a seemingly minor component. In terms of design, the driving factor this time was manufacturability. That was our main hurdle we had to overcome. There's definitely, better designs that we can do. That is not something that was in the scope this year, but that will definitely be further work in our CFD sort of design and analysis. Thank you. Yes?
Did you trade keeping your body diameter at a larger size versus the launch lug drag to understand how much of an altitude increase it gives you?
Another very good question. So the question of, was the trade-off worth it in the end for slimming down the body tube versus having to add those launch lugs for the, and then, having the consequences of having added those launch lugs, having the extra drag from those launch lugs. So in terms of that, it'll be the flight that tells, honestly, because the CFD that we've done, while quite good, still needs to be tested in the real world. From our rough design analysis, the
old design was okay. So we think that the old design with the old too big rail riders was okay. We're still testing out the new one, so we hope that that's okay. It will be tested in the flight, yes.
So yes, well, there was a last-minute change in the actual part that rides in the rail. For our design, it was going to reach 10,000 feet. From memory, yeah, the savings from the reduction of the diameter were very significant. I think we were gaining possibly up to 3,000 feet. 300, how many meters, does anyone remember? Sorry?
I'm not exactly sure, but I'll just clarify the percentages. The 30% drag on the lugs was 30% of the reduction. So it's like the remaining drag was 30% from launch lugs, but it's still significantly reduced because it's 30% from a 160 mil overall drag component. Does that make sense?
Yeah, so our drag was here, reducing the transition, brought it down to here, and then our launch lugs put it back some of the way, set us back some of the way. But from our analysis, yeah, like we were getting, I think it was 400 meters, so I can only think in metric, so about 400 meters of extra altitude from getting at least 400 extra meters out of 3,000, basically, meters, which is 10,000 feet, of extra altitude from slimming down our diameter. And yeah, we're pretty confident that based on our, so far, we're pretty sure it's good. Anyone else? Questions? Yes, please. Daniel, do you want to come up and talk about that actually? So, yes, our basic analysis, we just did like a basic sort of cosine curve with like an abrupt termination, not like a nice smooth termination like we've done. We are working on some more advanced simulation though, which I will let Daniel talk about.
So the problem is that there are more complex structures that OpenRocket doesn't account for and doesn't do very well. We've been using RocketPy, which is a Python simulation library that's just been released that works with drag curves, not with the rocket shape. So we're able to get the curve out of the fluids and then use that curve to run our sim, which will more tightly approximate the flight of this rocket, rather than just sort of having a guess like OpenRocket would do. So yeah, thanks.
Yeah, so did we repeat the question?
I think that's time.
Cool. So I think that's time. So yeah, thanks for coming, and yeah.